We're just waiting for a few more people to trickle in, and we'll get started in a minute or two. Hello, everyone. Welcome back, depending, to the second part of this year's distinguished lecture series in statistical sciences. My name is Martin Lisi, and I'll just begin by reintroducing the speaker and the DLSS. This is, the DLSS was established in 2000 by Don Dawson, who was the director of the Fields Institute at the time, and our very own Nancy Reed. It began at Fields and then moved over to CANSI. It's a prestigious award delivered annually, consisting of a general lecture, which we had yesterday, and a more specialized lecture today, delivered by an internationally prominent statistician or data scientist. The speaker goes through a rigorous selection process by the nominating committee, which is mandated to evaluate merit through the multiple lenses comprising CANSI's vision for impactful research in statistical sciences today. Our distinguished lecturer in statistical sciences for 2023 is Eric Joel Tchetgen Tchetgen. Dr. Tchetgen Tchetgen was raised in Yaoundé, Cameroon until the age of 12, and then went to boarding school in France. While completing his Bachelor of Science degree at Yale, which by the way was in electrical engineering and applied mathematics, he received a one-year travel fellowship to go to Ghana. There he used mathematical modeling to understand what factors are important to the adoption of a new hybrid maize seed. And this is said to be where Dr. Tchetgen Tchetgen realized that he could use his math skills to promote public health. When back in the US, he joined Harvard School of Public Health as part of an internship as a statistical programmer, and the rest is history. Again, I will go through some of that history for you here. He got his PhD in biostatistics from Harvard University in 2006, after which he served on the faculty from 2008 to 2017. And in 2018, he was named the inaugural Luddy Family President's Distinguished Professor in the Department of Statistics at the Wharton School of at the University of Pennsylvania. He has well over 200 papers in top statistical, epidemiological, and medical journals, having made numerous influential contributions to the development and application of statistical methods for missing data, causal inference, and semi-parametric regression in social, genetic, and infectious disease epidemiology. Just a few of his many awards: the Kenneth Rothman Epidemiology Prize, the Mirto Lefkopoulou Distinguished Lectureship, and most recently in 2022, the inaugural Russo Prize for Statistics, which is worth $1 million and is presented by Their Majesty the King of Belgium for Dr. Tchetgen Tchetgen's work on causal inference with applications in medicine and public health. So I now give you this year's PLSS speaker.
Thank you, Martin, for that generous introduction, and thank you for attending day 2 of the series, and thank you to Canty for selecting me for this prestigious award. I'm tremendously grateful for the opportunity to present my work. So today's talk is going to be more technical than yesterday's talk, but I'm going to try to keep it at a fairly conceptual level. I'm going to try to make a case that proxies are a useful tool for the analysis of observational data, particularly, but not necessarily exclusively, if you have causal inference in view. I've fallen in love with these tools. I found the application incredibly insightful. And so I'm going to try to convey some of that passion with this presentation today, titled Single Proxy Control. Let me briefly go through the outline. I'll start with some preliminary background remarks. Then I'll present a review of a standard assumption that's typically made when analyzing observational data for causal inference, so-called exchangeability or confoundedness or non-homogeneity bias, depending on which discipline you come from. So I'll start with a brief review of that, and then I'll introduce the control outcome calibration approach, which is a specific form of proxy analysis that I introduced a few years ago under fairly strong assumptions for identification. And what I'll demonstrate today is that, in fact, one can relax those assumptions quite substantially and obtain non-parametric identification under one assumption that's known as a completeness condition, which I'll try to describe, which is essentially the proxy needs to be sufficiently relevant for latent factors that induce bias. And so this completeness notion tries to formalize that idea. And I'll go over an application early on, and I'll come back to it later on to illustrate how the methods could be used in practice, and some concluding remarks. So let me, I don't think I have time for this. I included the material in the slides, which is how to relax this completeness assumption. I'll make some remarks about it throughout, but we'll not cover those slides, but they're there for anyone interested. I'm assuming the slides will be made available. So on measure confounding, which is the topic I'm going to focus on today, on homogeneity bias, is a well-known threat to valid causal inference from observational data. An approach that is sometimes used in practice to assess residual confounding bias is to check whether known null effects can be recovered free of bias by evaluating whether the exposure or treatment of interest is found to be associated with a so-called negative control outcome upon adjusting for observed confounders. An observed variable is said to be a negative control outcome, and I'll use the acronym NCO throughout the presentation, or more broadly, an outcome confounding proxy, to the extent that it is associated with hidden factors confounding the exposure outcome relationship in view, although not directly impacted by the exposure. So with this definition in mind, therefore, a negative control outcome, which is empirically found to be associated with the exposure, might suggest the presence of residual confounding, because that would be a surprise finding, as the exposure should not be causally related to the outcome. If you find it to be associated, that indicates that perhaps this is a spurious association, and you might worry about residual confounding in your application. In fact, NCOs are not a new idea. They've appeared in the literature as under different names: falsification outcomes, endpoint, control outcomes, secondary outcomes, supplementary responses, unaffected outcomes, donor pool in certain control literature, or proxies, and actually in statistics, randomized trials, placebo outcomes or placebo groups. So let me just give you a little bit, just to illustrate how common these have been used. I'm going to give you spend a little bit of time going over a list of existing application of negative control using in epidemiology to detect the presence of potential confounding or measure confounding. So for instance, papers in flu vaccination literature looking at outcome being defined as elderly hospitalization, and often the NCO in those settings are injury or trauma-related hospitalization. And the idea here is that the vaccine should not be protective against injury or trauma, or should not be associated with it if you're correctly adjusted for any confounding factors. And if you find them to be associated, that might indicate that there are confounding concerns. I talked a little bit about healthcare seeking behavior as being a major confounder of concern in this setting yesterday. And so this would be such an analysis that will try to assess the extent to which that's a problem. I also spoke a little bit about COVID vaccination being an exposure of interest, the outcome being COVID infection. And as an NCO, flu or RSV infection has been used as a negative control outcome, again, to detect whether or not there is any residual confounding in the analysis. Shifting gears a little bit in the cancer literature, exposure might be mammographic screening, an outcome then breast cancer incidence, and the NCO there would be competing reasons for deaths from other causes that may not be causally related with mammographic screening, and therefore if you find an association, that would again be indicative of spurious correlation, spurious association and not causal relationship. Continuing in a different setting, air pollution, where one might be interested in the causal effect, the health effect of PM 2.5, particularly matter 2.5, or other kinds of air pollutants on elderly hospitalization. And an NCO there often will be, because they have time series data, looking at history of elderly hospitalization prior to the measurement of PM 2.5. And because of the time ordering, one should not expect PM 2.5 to be causing elderly hospitalization. And if one were to find an association, that would be indicative of perhaps confounding being present. So these are a range of examples across different areas of epidemiology. The one I'm going to, there was another air pollution one, I'm going to skip that one, and I'm going to arrive at the one that I'm actually going to discuss today. This is one where we're interested in the impact of Zika virus on birth rate. And the NCO will actually be birth rate for the prior year as an NCO. So as I mentioned, we'll use this example for illustration today. So let me give you a little bit more about the context. This was in Brazil during the outbreak of 2015, the Zika virus outbreak. And 673 municipalities are included in this analysis that I'm interested in. About 180 municipalities experience high incidence of Zika, and so those are going to be known as the exposed units. So the unit of analysis is a municipality in this case. And then a little under 500 municipalities were controlled as they reported no Zika virus in case. The Zika virus, which can be transmitted from a pregnant woman to her fetus, can cause serious brain abnormalities, including microcephaly, also known as an abnormally small head, and therefore also lead to stillbirth often. And so this is the pathway through which the Zika virus might lead to a reduction in birth rate in a given region. And that, therefore, one is interested in asking whether the Zika virus outbreak actually caused a drop in the birth rates in Brazil, in affected regions of Brazil. So that is the epidemiologic question of interest. The data we had was actually not very rich data that we had access to, and we had birth rate per region. Chen Park, who is a postdoctoral fellow who did the empirical analysis for this paper, went out and got some data on the various municipalities in summary data, various municipalities in Brazil, and tried to incorporate those data in the analysis to adjust to the extent possible for some differences between affected regions and unaffected regions. But a crude analysis, which is also fairly consistent with one where you would adjust for the covariates that he was able to collect, suggests that, in fact, the Zika virus was associated with an increase in birth rate, not a decrease in birth rate. And in fact, there was about a 3 birth per 1,000 people, and this was a significant statistical significant finding. And this was, of course, a surprise finding. It was counter to what we expected scientifically to occur. And certainly it would not be the right public message to put out there that in fact Zika virus was protective against stillbirth. Now, so using this idea of an NCO, we had access to the birth rate in Brazil the prior year. And so we just checked, one could just go ahead and check whether in fact there is an association between Zika virus and birth rate when there was no Zika virus circulating. Okay, so again, we drew the comparison between these two regions that in 2015 were affected by Zika virus and those, the controls, and we looked at the association between that exposure and the prior year when no Zika virus was circulating, the birth rate that year. And we found again that there was a significant association with controls having higher prior rates, suggesting that in fact, there are some concerns about confounding, residual confounding bias in this analysis. So once you have some evidence that they may be biased, the next question, natural question, is what can I do about it? Can I reuse these NCOs to try to adjust for that bias? And that will, in fact, require additional assumptions, right? Detection or testing is much easier of a problem, a statistical problem, than bias correction. And so the question is, what kind of assumptions are reasonable in this setting? And it turns out that one really, really old method that's been around roughly since the 19th century by John Snow is the difference in differences approach, DID. And this is, in fact, can be interpreted as a negative control adjustment method. And that is, DID essentially looks at the change in birth rates for the exposed from the prior to the recent year and draws the same change for the controls, and then takes the difference of those differences. That's the name difference in differences. And the idea is that if there's no confounding that doesn't change over time that you haven't measured, on the additive scale, it will be canceled out by taking that difference. So from an NCO perspective, this assumption that there is the confounding bias is constant across time is often which is often described as a parallel trends assumption. As an NCO, from an NCO perspective, this can be interpreted as an additive equiconfounding assumption, which essentially states that the degree of confounding, of unmeasured confounding association with the outcome of interest is the same as the degree of association on the additive scale with the pre-treatment outcome. And so that's another way of rephrasing additive confounding. Another second assumption that's really important to DID is that there is no anticipation bias. That is that the potential outcome, that the outcome prior to the treatment cannot causally be affected by the treatment. And so that is an NCO assumption. And that's usually taken for granted in DID analysis because the negative control outcome, which is the pre-treatment outcome, comes before the treatment. But it is an assumption because there is a no anticipation assumption there that individuals who receive treatment did not anticipate receiving treatment and therefore change their behavior, which will be a form of reverse causation. Okay. And so that assumption is an NCO assumption. And then what DID does, it adds to that assumption an assumption of parallel trends to then debias the estimator. In practice, equiconfounding or equivalently parallel trends may not be a reasonable assumption for a number of reasons that are very well documented in the literature, including if the outcome trend is also impacted by an unmeasured common cause with the treatment. So essentially what DID does, it takes the difference, the change in your outcome, and it says that change in the outcome is not confounded. And then it analyzes that the change using the outcome, the change in outcome as the outcome, it analyzes using observational data methods, okay, under this unconfounded assumption. And so if the trend itself is also impacted, not just the level, but the actual changes are in fact impacted by residual confounding, parallel trend will not hold. I think this is one of the most important departures from parallel trends. Another important departure from parallel trends in the context where you're willing to, you wish to generalize this idea of an NCO. So you're not just going to restrict yourself to pre-intervention outcomes. You might have other outcomes that you know are valid NCO, might be valid NCO. Is that those outcomes may live on a different support. You may have a continuous outcome, but your negative control outcome is binary. And so this parallel trend assumption, which is on the additive scale, there is no reason why the degree of confounding on a binary outcome will equal the degree of confounding on a continuous outcome. The former is bounded between -1 and 1 because the outcome is binary, and the latter is not bounded at all. So they live on very different scales. So DID, the parallel train assumption, will be nonsensical in that setting and often violated. It would often imply that your outcomes, the probability of your outcome would have to be outside of the 0-1 range, which a priori we know cannot hold. So back in 2014, I was struggling with this issue of how do I correct for bias when my NCO may or may not be a pre-treatment outcome if I'm not willing to make the simple parallel train assumption. And so I wrote a paper that was primarily meant for an FP audience. This was published in HAE, where I introduced this approach called control outcome calibration approach, COCA, a bit of a catchy name for something that's supposed to be a healthy outcome. Okay, as a simple yet formal counterfactual approach to the bias causal effect estimate in observational studies. And COCA essentially, I'll come back to this, essentially treats the negative control outcome variable as a proxy measurement for the source of confounding. And the source of confounding here is being refined to be the underlying potential outcomes. And I'll come back to this in a few slides. So this assumption formalizes the idea that as a relevant proxy of residual confounding, the NCO would be made irrelevant to the treatment assignment mechanism if one were to hypothetically condition on the underlying source of confounding and treating the potential outcomes as the ultimate source of confounding. And again, don't worry about it right now because I'll come back later to this with some pictures to sort of illustrate what I mean by these words. What I do want to say is that for inference, the approach that I developed in 2014 involved correct specification of a regression model for the negative control outcome condition on the treatment-free potential outcome, together with a rank preservation assumption. So rank preservation is basically a constant treatment effect that every individual in the population experiences exactly the same causal effect. In the health sciences, that's often not a reasonable assumption that the treatment effect is constant because we expect quite a bit of heterogeneity across people. Particularly with treatment, we expect people with particular genotypes may actually react to the treatment very differently from people with a different phenotype, even if the genotype is not a confounder. So there's a lot of underlying heterogeneity and rank preservation rules that out. So this was a simple approach, it's simple to implement, but it often will be deemed unrealistic. So in today's talk, I want to introduce a nonparametric extension of this approach, COCA identification and inference about the average causal effect for the treated. As we show, COCA identification is feasible without the need for rank preservation and therefore a constant treatment effect, therefore accommodating arbitrary degrees of effect heterogeneity across units. I do want to mention that I have been doing a lot of work in proxies, and we have a recent series of papers on so-called proximal causal inference, which leverages a pair of proxies or negative control treatment and outcome control variables to non-parametrically identify treatment effects subject to residual confounding without invoking a rank preserving assumption. So I do mention this just to point out that this is actually a very different strand of work. While proximal causal inference relies on two proxies, COCA is a single proxy approach. It only requires one proxy. And the definition of proxy is slightly different as well. The proxy relevance is going to be a lot more refined. And so we'll require further thought about reasoning about whether or not it's a valid assumption. For estimating inference, there are three methods that we developed. I'm going to spend quite a bit of time on just talking about the first one, extended propensity score. So propensity score approaches are very well-known methods. I discussed them a little bit yesterday. And so we have an extension of that. I'll explain how that is to account for unmeasured confounding using proxies. A so-called outcome calibration bridge function, which is a proxy version of an outcome regression approach to adjusting for confounding. And then the doubly robust approach, which I'm not really going to discuss due to the time limitation, but I'll briefly mention and illustrate in the application, which combines these two methods and is likely to have smaller bias if you're using nonparametric estimators, but also has this property that you only, in principle, need one of the two approaches to be correct to recover valid inference about your causal effect. So very briefly, let me review this idea of exchangeability. Actually, so the context is we're going to aim to identify the so-called average causal effect for the treated. And if you're not familiar with counterfactual notation, what I want you to imagine is a hypothetical intervention where you're looking at only treated individuals, people who actually happen to have been infected with Zika or to live in a region that was infected with Zika, where Zika was present. And you imagine a hypothetical intervention where, of course, you know that all those people were exposed. So this outcome would be the observed outcome under fairly mild assumptions. So the potential outcome is what would happen if you could force those people to be exposed, something very unethical, but that's okay because they were already exposed. And so we just have to agree that, oops, that the outcomes that match, that this outcome matches the observed outcome. And the less controversial question is, among those who were exposed, you have to imagine, stretch your imagination and define an outcome. What would have happened to them had they not been exposed? And that's the potential outcome. So this is a useful exercise because then the contrast between what actually happened to them, given that they were exposed, is made with what would have happened to them given if they had not been exposed. And of course, contrary to fact. And so this is not an observed outcome in this population, and we need to learn how to extrapolate the observed data to learn about this potential outcome. And therefore, this is where stands the controversy of causal inference from observational data. It is a dangerous enterprise, and you need strong assumptions for this extrapolation. So the standard assumption that are typically made in causal inference is consistency. This is the story that I gave, that the observed outcome matches the potential outcome for this hypothetical intervention. It is an assumption that does not always hold. It requires having a well-defined exposure, and also often makes an assumption that the exposure of other units cannot affect your outcome. Positivity, that for any covariate value, L are going to be the covariates here that is observed in the data. There's at least one individual that takes the outcome that you're interested in. Sometimes it's referred to as an overlap condition. And then exchangeability, which is an assumption of nonparametric confounding. And the idea here is that under standard causal inference assumption that you measured enough covariates such that the treatment is effectively as good as randomized, and therefore independent of all unmeasured baseline covariates. And you can think of potential outcome as baseline, the ultimate baseline covariate that has not been observed. So for people who were treated, we imagine that before they even received the exposure, not treated, the exposure here is Zika virus, that they have both outcomes exist. The potential outcome, what would happen to them if they were exposed, and what would happen to them if they weren't exposed. And so these are pre-treatment variables. One of them is revealed, the one that, given that this is the treated group, the exposed group, the one that corresponds to that outcome. And the other one is the counterfactual. And so the standard assumption is to assume that the potential outcome is independent of the treatment given L. And so essentially within levels of L, you have a random sampling to decision for whom you will view y equals 0 and y equals 1. And so by simply reasoning under random sampling, non-measure confounding essentially assumes that you have a conditional randomized trial, that nature ran such a trial. And so this requires measuring all relevant confounders. So this is the standard idea of exchangeability. Another way to interpret it is that the individuals who are treated are a priori comparable to individuals who are not treated or not exposed. Okay. And this is made within covariate values. Under these assumptions, one can show that the effect of treatment on treated, which I'm going to refer to as beta, can be obtained from the empirical distribution by regressing y on the covariates among the treated, y on the covariates among the controls, and then averaging that difference with respect to the distribution of the covariates among the treated. This is a form of direct standardization. Okay, so this is nice. It's a statistic. It's only expressed in terms of observed data. And so it becomes a statistical problem, and statisticians have studied this problem over the years. So today I'm going to depart from that, and I'm now going to make this strong third assumption of unconfoundedness or exchangeability. And I'm going to suppress L, because it's really not that relevant. I could incorporate them in any analysis I do, so I'm going to suppress them. And I'm worried that they have an exposure and outcome, and then there are latent factors that correlate the two in pathways that are not causal. Okay. So I represent them as a Borg, as here. Instead of making an assumption of ignorability or exchangeability, we'll presume that one has measured a valid so-called negative control outcome, or more broadly a proxy, which I'm going to denote as W, which is known a priori to satisfy two formal conditions. The first condition is that W must be associated with the mechanism leading to the residual confounding. So in the COVID-19 or flu example, the confounding concern was in fact healthcare seeking behavior. And so we could use trauma or injury, admissions to the hospital for injury, as a marker for that, or historical vaccination records. In the Zika virus, we're going to use the pre-exposure birth rate. And the idea is that if there are any confounding of that leads, any factors that lead to differences in the regions, which are actually very different regions, the ones that were exposed to a lot of Zika and the ones that were not, that those differences will also equally be correlated with the pre-intervention birth rate. And so this idea of pre-intervention birth rate as a valid proxy or negative control outcome is quite natural in that setting. And then we will need this exclusion restriction that W cannot be causally impacted by the treatment of interest. So the first assumption is one of relevance, that the proxy must have some information about what is the factors, the measured factors that are not observed, but it's not complete information. So just adjusting for it in your model will not explain away the bias. You have to use it in a very different way. And the way you use it will require a second assumption, that in addition to be relevant for the source of confounding, that the proxy cannot be causally impacted by the exposure. So these can be formalized with potential outcomes by the exclusion. The second assumption can be formalized by saying the potential outcome, if I were to intervene on A, is the same as the observed outcome. It doesn't matter on the value, it doesn't matter what the value of A is. So that's encoding the second assumption. And then the first assumption is going to be encoded with this condition, dependence assumption that W needs to be associated with the potential outcome Y equals 0. Now, the reason I think this is a refinement of the relevance assumption is for the following reason. Imagine that you were a doctor and you're thinking of assigning a treatment to patients, okay? Let's say you have an HIV patient in front of you and you have to decide whether or not to treat the patient. So usually what's done in those settings, and this is what we imagine will be done in the settings where you use these methods, is that the physician would try to imagine what would happen to that patient if they did not receive the medication. Would they die in a year? Would they die in 5 years? And that is a potential outcome. That's exactly why A equals 0. And that's what's driving the decision to treat the patient or not to treat the patient. And so if you imagine that you haven't measured all those records, the proxy would be something that would be associated with that prognostic. What would happen to the patient if they did not receive the intervention, the life-saving intervention? And so you would want YA0 as possibly the stronger indicator of residual confounding. And it's unmeasured because YA0 is not measured for people who are treated. It's only partially measured in the subpopulation of people who are not treated. So this is not a testable assumption per se. The second assumption that we are going to make with COCA is that now thinking of YA equals 0 as the ultimate source of confounding is that if you had measured YA equals 0, it would render W irrelevant for confounding adjustment. And the best way to encode that is that W is no longer predictive of the treatment. So in a propensity score method, W would fall out of the model if you measured all the confounders, in particular if you had measured the potential outcome of the no treatment. And so following with this reasoning, you can illustrate this reasoning with the following graph. So this graph is encoding the fact that YA0 and YA1 are my ultimate source of confounding and therefore affect A. The red arrows here encode the fact that all three variables deterministically determine the observed Y. Why is that? Because my observed Y will be Y equals 0. If Y equals 1 if I were treated, and Y equals 0 if I were not treated. And then the proxy, the most important part of this graph is illustrating that the proxy is meant to be a refined proxy of the potential outcome of the no treatment. And so, as you can see from this graph, if you're familiar with these separation arguments of graphical model, you would conclude from this graph that in fact, if I were to condition on YA equals 0 alone, that would screen up W from A. So as I mentioned, there are many examples of negative control outcomes that could be reason to potentially satisfy these assumptions. And in the DID case, the pretreatment outcome is such an example, but DID, as I mentioned, will require an additional confounding assumption. An assumption we're not going to make, we're going to replace with this conditional independence assumption, which is more aligned with the thinking of W as a proxy. All right. So what did I do in 2014? What I did is essentially assume an additive model, a very simple, understandable additive model. Again, this was meant for primarily an epi audience that was sufficient familiar with linear regression to understand what was going on. And so what this is telling you is that your observed outcome would be y equals 0 if you were not treated, so A is 0. That's just consistency. And the assumption is that for any given person, if you're treated, your observed outcome would be y equals 1, which is just y equals 0 plus psi naught. And therefore, psi naught is a causal effect. And you could see why this is a strong assumption that the right-hand side is a random variable and is assumed to be constant. So this is the assumption of no effect heterogeneity across individuals. That is a strong assumption, but that was the assumption I was willing to make in 2014. Under this model, what was known in that paper is that, in fact, what you can then do to find psi 0 is you can try to generate the potential outcome of no treatment. How would you do that? Well, you take the observed outcome, and if a person were treated, you remove a guess of psi. So I'm going to guess that psi, the true psi, is 2. I put 2 here. People who are treated, I remove the number 2 from the outcome. People who are not treated, I don't do anything because the outcome is y is 0. And the idea is that once I do this operation, y psi is well defined for everyone. And then I simply check whether a condition on y psi deseparates W and A. Why is that? Well, because I realized that by my prior assumption, this defining assumption, y psi would recover y equals 0 if and only if psi is at its true causal value. And so this exercise is a very simple exercise that one could implement using a regression model. In fact, one could just run a regression of W on y psi and A for fixed value of psi over a grid. And then you would test the association between A and W in that model. And this is called inverting a test for the null hypothesis that A is independent of W, given Y. And you would keep all values of psi that, in fact, you failed to reject that null hypothesis. Right? It's an old trick in statistics called inverting a test statistic to construct a 95% confidence interval. Okay. Now, I mentioned that there are a lot of limitations with this approach, notwithstanding this assumption that the treatment is constant. And so I aim to, today, what I wanted to present in the remaining 20 minutes or so is how one could go about relaxing the assumption so that you no longer rely on a constant treatment effect. So the first approach, I'm going to spend a little bit of time talking about 2 approaches. The first one is so-called extended propensity score. Propensity score is a model for the treatment, the propensity to be treated. And so treatment is binary, so such a model will require just specifying a model for the probability of A equals 1. And because there is confounding, I'm allowing from confounding, that probability will in fact depend, on your potential outcome. Recall that under exchangeability or no confounding, the potential outcome will be assumed to be independent of A. So the departure of that actually can be checked by ensuring that the propensity score, encoding that the propensity score may depend on potential outcome. Why is this an important property to recognize on our measure confounding? Is that in fact, if you recall, let me just focus on this formula for a second. The target of inference is this difference. And the first term in that difference is identified by the outcome mean, observed outcome mean in the treated. And the second one is the problem, is the one that's not identified. But one can show that if you in fact knew pi, this extended propensity score, one could simply identify the programmatic counterfactual mean by a reweighting trick. And this is sort of an inverse probability weighting expression where the propensity score now has been replaced by this extended propensity score. So this is just simple algebra ensures that this hold if you knew pi exactly. And so the point of what I'm going to demonstrate is that I can actually see, if I knew pi, I could use this method to identify my causal effect. And so what I'm going to now demonstrate is that with an NCO, you can nonparametrically identify pi. And then I'm home free. So as pi is unknown, we next demonstrate that how to leverage an NCO assumption to identify that pi. For that, we're going to require an auxiliary propensity score, which is a propensity score where you simply regress your treatment on the NCO. So that's based on observed data. And our first result is that under consistency of my NCO assumptions, these are all untestable assumptions for the most part, except maybe the relevance assumption. We have the following identifying formula for pi. It turns out that pi satisfies this formula, that if you knew pi and you took the odds of pi, recall pi is probability of A equals 1 given y, A equals 0, potential outcome, evaluated at y. If you were to take the, and so this is an odds, and this is another odds now conditional W, that the odds conditional W for the treatment conditional W can be recovered by taking the expected value of the odds conditional on the potential outcome, evaluated at the observed outcome, integrated with respect to W of y given W in your exposed. So the reason this is an identification result is because, in fact, I know how to learn this from the data without any assumption. The expectation here is with respect to a density of y in the unexposed, which is observed. And so I have an equation with one unknown, which is pi. The hard part is this equation is an integral equation. The unknown is buried under an integral. So on the one hand, I know that this equation admits at least one solution, but I do not know a priori that it admits a single solution. The solution may not be unique. How do I see that? Well, it might be possible to add an arbitrary function of y in here, provided that function of y has mean 0 given W and A equals 0. Does everyone see that? So I take my odds and I just simply add a function of y, let's call it ty, and I tell you a priori that that function of y has mean 0 given W and A equals 0. So I'm effectively adding 0 outside of the integral and rewriting it as a function. So that would mean that my odds plus that function of y also solve my equation. So I have at least two solutions. And that is a problem because the solution I need is this one. All right. So we therefore have the second result. If assumptions that I give you result one whole, the net value in zero, and the equation 12 happens to have a unique solution, then pi will be nonparametric identified and the observed data by the observed data, and in fact the effect of treatment on the treatment will be identified by this formula, which is now an empirical expression where pi can be expressed with respect to the observed data. Now let me say a little bit about this idea of a unique solution. So equation 12, which is this important equation I'm going to leverage, is known in mathematics as an integral equation, more precisely a Fredholm integral equation of the first kind, because Fredholm was the first person to study such integral equations. This has been extensively studied by mathematicians who study functional analysis. And so conditions for existence of such solutions have actually been and uniqueness of such a solution have been very well studied. This study also comes up in econometrics, in a so-called nonparametric instrumental variable model. And there again, they've also been studied. And it also comes up, this type of equations show up in proximal causal inference. And we've documented conditions for existence and uniqueness of a condition. I'm not going to go over those conditions. I will simply say that in practice, there's a sufficient condition, which is to rule out the kind of problems that I mentioned before, which is that in giving your data sharing mechanism, it has to be that, oops, sorry, I think I took that out. It has to be that any function of y that has mean 0 given W and A equals 0 must be 0, in which case you cannot add any function to solve this equation. Okay. So that is a completeness condition. That condition is easiest understood with discrete data. But that condition would effectively say is that if your y has 3 levels, your W must have at least 3 levels. And that kind of makes sense because I'm solving for a function of y. So if y has a support that's larger than W, I cannot solve for y, there will be multiple solutions. And that's also known in statistics as a rank condition. Because essentially with discrete data, this becomes a matrix equation and you have to be able to invert. So your matrix must not be avoid being rank deficient in a particular manner. So intuitively, that's what we mean. And then for continuous data, you need to appeal to this idea of completeness. And so I'm going to make that assumption for the presentation today, but that assumption can be relaxed. Okay, I want to spend 5 minutes talking about an alternative approach. If you're not comfortable using the extended propensity score, here's an alternative approach that's actually quite intuitive. So the approach is going to require the following condition: that there exists a function of W of your NCO, such that if I took that function and I integrated with respect to W, conditional on Y and be untreated, I would recover Y. So again, this is an integral equation that I would want to find such a function, but if it were true that such a function would exist and they were unique, I could solve this integral equation. Now, why is this more intuitive? Well, if you look at the counterfactual intuition behind this equation 13, what it's saying is essentially a W is a proxy, it's a valid proxy, and I want you to think of it as essentially I have a measurement error problem. And W can play the role of a mismeasured version of the counterfactual outcome, but my measurement error is not too bad, too severe. It's bad enough that it requires nonlinearity. So that there exists some transformation of W such that if I were to take that transformation, I would obtain an unbiased model for Y, conditional on the true Y. Well, this should ring a bell because in fact, the most basic measurement error model satisfies this assumption. Classical measurement error is if W were in fact just the potential outcome plus independent mean zero error, it would in fact be the case that equation 15 is satisfied for such a choice because I could take the mean of W given Y equals 0. On the right-hand side, Y equals 0 is a constant, and the mean of epsilon given Y equals 0 is in fact 0. So classical measurement error is part of this model. So effectively what we're doing is we're saying our proxies are sufficiently rich so that there is some transformation of them that somehow gets rid of the measurement error and we recover the outcome of interest. But this is not a one-to-one map. There may be many function of B of W, and that would be okay. And so we then have this result that if you're able to find such a solution, B star of W, then you can take that solution and simply integrate it with respect to A equals 1 in the A equals 1 sample and recover the causal effect of interest. And so we have two different ways of tackling this problem for identification. And the important part here is that, in fact, unlike the extended propensity score, here we do not require a unique identification of B star W. It can be any solution. We'll still recover identification. And this is nice because we just need to find one solution. All right, let me talk a little bit about estimation, and I might just skip the double robustness. So for estimation, I'm going to focus on B. How do we do estimation? After all, this is a statistical talk. I've just been talking about identification. So we've resolved identification. We now need to solve these integral equations. Fatal integral equations of the first kind are notoriously ill-posed. They're very unstable. That means any variability, uncertainty in the space of the density defining the integral equation. So recall the integral equation is an expectation. So think of the conditional expectation as an operator, but it's one that you have to estimate. So any uncertainty in that is blown up in solving the equation. That's what we mean by ill-posed, is that it doesn't do well with statistical error. So any residual bias in your sample will be blown up in your solution, and therefore it becomes intractable. So rather than directly solve for it, we took an approach that's come out of the modern machine learning literature, which is to use adversarial learning. And the way we encode this problem as an adversarial learning problem is to, if you just squint a little bit, you will note that what I have here, this residual of Y minus BW, is multiplied by 1, the indicator of being in a control arm, so having A equals 0, and then a function of Y. And in fact, this equation is a reframing of the integral equation. And to see that, just take the expectation of the equation conditional on A equals 0 and Y. And I would say the mean of Y given A equals 0 and W is equal to the expectation of BW given A equals 0 and Y equals 0. That's exactly our integral equation. And so the way we're going to enforce a solution is we're going to take that integral equation and we're going to replace the conditional expectation by multiplying by a rich set of functions of Y. And we want to stress the system, we want an adversarial choice of Ty that's going to make this expectation as large as possible. So that's a max over a set T. T can be a large space or a small space, depending on your taste. And then we're going to find the B that minimizes at maximum. This is known as a minimax operation. We need a T-square here to ensure that the objective function doesn't blow up, and we turn this into a saddle point problem. And we need penalties to further regularize the problem. And so this is a really nice trick that we learned from machine learning, because then H and T just determine a functional spaces that can be made sufficiently small or large depending on the data and the ill-posedness, degree of ill-posedness of the problem. And the penalty is essentially acting like a Tikhonov regularization. PyStar can likewise be solved using this minimax approach. And it's equally nice, appealing approach because H and T can either be finite dimensional, so parametric models like linear models, or could be infinite dimensional. And we've used reproducing kernel Hilbert space to do this. One could use neural networks if that's what you fancy. And it naturally feeds into the adversarial learning of such methods that's been popularized in such methods. All right, so one could also construct a doubly robust estimator. I'm just going to mention that, and I'm not going to stress over it, and it would have small bias. All right, so let me close by going back to the application. If you recall, we're looking at Brazil, and some parts of Brazil were affected by Zika virus, some parts were not. And we want to know whether that had a causal impact on the following year's birth rate. Recall that a crude estimate found that, in fact, it suggested Zika virus was protective against reduction of birth rate. And the COCA approach actually completely flips the sign and finds that, in fact, the Zika virus, as one might have expected, had a significant effect on reduction of birth rate in Brazil. Interestingly, we also implemented a difference in differences approach, and it also flipped the sign in the direction that we would expect scientifically. But the effect was somewhat attenuated compared to ours. Now, I'm not claiming that ours is better than DID because the assumptions are not strictly nested. In a low noise setting, parallel trend would in fact imply our assumption. In that sense, our assumption will be weaker than parallel trends, because whenever parallel trend would hold, our assumption would also hold. But our assumption may hold without parallel trends holding. So in that case, in a low noise novel setting, they would be nested, but in general, they're not. And so what we actually suggest is reporting both, including the crude. And the idea here is that in terms of chasing bias, it's actually better to try to address or measure confounding using a technique that does not rely on known measure confounding than to simply use known measure confounding. Okay, the more estimators we have, an agreement across estimators, the better we are at drawing some conclusions. So it's time for conclusions. COCA offers an alternative approach to address residual confounding with a single proxy, therefore adding to our existing bag of tools using proxies. And I have to draw some comparisons. So we have instrumental variables is another set of tools. So relative to instrumental variables, we do not make a monotonicity assumption. We do not make a homogeneity assumption that are typically needed for identification. Relative to DID, as I mentioned, we do not make an equiconfounding assumption or a parallel trends assumption. And relative to proximal causal inference, we require one proxy and not two. But of course, we do make an assumption that these methods do not necessarily make. So COCA also is, this is a little bit of a big term, but it is universal in a very specific sense, in the sense that it can be used to identify any causal effect on a tree that can in principle be identified under exchangeability or confoundedness. So quantile causal effects, hazard ratios, all of those methods that under confoundedness can be identified, there is a corresponding method to identify the same measure in the tree that using COCA. We also have developed methods for sensitivity analysis. It's important to interrogate the sensitivity of your methods to your assumptions. And so those are included in an EPI paper that we wrote on the topic. And there's much work that remains to do with COCA. And I hope this will inspire some of the talented statisticians in this room to maybe look into it. There are really interesting problems in causal inference that are really purely statistical problems of inference. but very different from classical statistical problems in the sense that the objects of interest are somewhat different, it's differently motivated. And so one does not need to believe in counterfactual and causal analysis to find some interesting statistical problems within the literature of causal inference. So I just want to thank the NIH for supporting this research. I want to thank my co-authors, Chen Park and David Richardson. I want to thank Jamie Robbins, Thomas Richardson, Amir Ghazami, and Ilya Spitzer for really, really helpful, insightful discussions about this work and its usefulness for causal inference in the health sciences and other sciences. Thank you so much for your attention. I'm happy to take any questions.
Let's start with a question from the audience.
So I was just thinking, you had a slide where you compared the COCA approach to the, you compared the COCA approach to the DID method, but I'll be wondering, a newer method used in econometrics is a synthetic control. And I was wondering, what if you could make a synthetic control of the other countries that were not affected by the Zika outbreak relative to the country that was affected by the Zika country, and how would it compare to this approach?
That's a great question. So synthetic control, just for folks who are not familiar with it, what synthetic control will say is they don't believe in parallel threads. And what they will do is they will construct, because you have one, let's say you're only going to use Brazil as a treated country that's being exposed, and you're going to find countries that were not affected by Zika as controls. But rather than just comparing them to Brazil, you're going to find in the period before the Zika epidemic, you're going to run a regression of Brazil's birth rates prior to Zika, run that regression on those other countries' birth rates. Construct that regression, and that's called a synthetic control because in the pre-intervention periods, it matches Brazil. And then you use that to extrapolate and learn what would have happened to Brazil in the post-intervention period. So this requires many controls that satisfy the no spillover effect because the controls cannot be causally affected by the intervention. So whereas I'm taking time to impose that, that will require that even in the post-intervention periods, there's no spillover effect of, this is Zika. This was a global pandemic. It wasn't just Brazil. So that's the first issue. The second issue is it would require having many years of data on all of these countries in the pre-intervention period. One could go out and look for them, but that is the data requirement. Now, very briefly, there are identification conditions for synthetic controls. The identification condition that synthetic control makes is that, in fact, in the pre-intervention period, you can have a perfect fit, not just a regression. You look at the residual error, and that residual error should be 0 in your regression. I've never seen a linear regression that has 0 pre-treatment error. Now, to be fair, the authors of those methods say the method should only be used when there is a pre-intervention good match. But they don't define what a good match is. What they mean is when that error is small and all the math assume that error is 0. Finally, I will say that we have developed synthetic control methods that do not think of the donor pool as donors, but think of them as proxies. We have formalized identification assumptions that do not require a perfect match on potential outcome in the pre-intervention period. And so there are versions of proxies that could equally apply if you have the data and you were willing to make the assumptions to a synthetic control setting. And I'm happy to discuss that after the talk, but hopefully that answers your question. Thank you.
There was another question over here.
Thank you so much. My question is more about the wording saying W need to be associated with the confounder or measure confounder. When I listen to that, I'm like, first, I think W need to be maybe the descendant of the U, but not a parent. Or because if it's a parent, it will not work, right? If W is a parent of the potential confounder when non-treated.
Yeah.
So when you say associated, I don't know if it's just a wording or if maybe it's because we wanted to highlight other potential scenario there. I think it might be connected also with equation 16 with the measurement error. So
Yeah.
if
Yeah, that is a great question, and it's not a coincidence that these arrows or there's a reason the arrow is in the direction. You're exactly right. So this is about the causal story of what these arrows mean. So let me first say that I'm ignoring you here. I'm taking a position where I'm assuming all causes of y, the worst case scenario, that anything that predicts y is a confounder. So this graph is meant to represent that limiting. Because when you're thinking about the confounding itself as being the potential outcomes, you're really thinking that everything that causes the potential outcome is a confounder. And this is how you encode it. So that's a very extreme case. So we're going to correct for the worst case scenarios. We're being very conservative in that sense. Now, there is a problem, as you say, that if this arrow, in fact, were due to an unmeasured common cause between W and Y equals 0, conditional on Y equals 0, I'd have a collider through this pathway. And so that independence assumption would not hold. And you're absolutely correct. That is true. So the storyline, the narrative has to be that you believe this. However, even if you don't believe this and you do believe there's a bull arc, there are situations where this approach will still be useful, mainly if the confounding is primarily driven by Y equals 0 and this arrow is not present. Then in fact, the collider bias will be mute because it will be adjusted for. The mental model that I have when I work with my collaborators and I explain these methods is essentially I'm thinking of W as I'm thinking of unmeasured confounding here and the proxies as a measurement error problem. So forget about the graph. I want them to think about, well, W's, your W's, you're thinking of them that there's on some scale, they measure something about your outcome. You don't know what it is, you don't know what the scale is, that's the BW. But you imagine that on some scale, they measure something about your outcome and you want to find that scale. So I think the narrative of measurement error is a useful narrative. It moves away a little bit from the causal story and it hides some of the issues with the causal story, which you're highlighting. And so this framework is not free of issues. No, all the methods will be the same. It's a nonparametric measurement error method. So this is the classical measurement error was just to illustrate that it falls within this class. But because B of W is allowed to be any function, and that we only require one such function should exist, it's non-parametric classical error problem.
Online audience, real audience. In person, I mean, in that case, let's thank Dr. Tchetgen Tchetgen again as we close the DLSS 2023.